Wasabi, you guys. Welcome to Integration Bee Training for Advanced. This is part 9.1, and in this section we're going to be learning about infinite functions. Yes, infinite functions. We're going to dive into some very fun stuff now. The most satisfying part of all integration bees is dealing with infinite functions. So let's go ahead and get into this. So you've probably seen this before, right? This integral that's just constantly being square rooted inside another square root inside of another square root. So here's how the concept goes. So the way we deal with infinite functions is we let this whole infinite function equal to like w or omega or some constant, whatever. Okay, so for now I'm gonna use omega because this is just how I first learned it. So when we let this equal to this infinite function, okay? Now let me ask you this. Is it true that the inside is equal to the outside? Right? It's very for beginners, it's a little puzzling. But if you think about it, you know, it's technically true, yes. The inside does equal to the outside. And so because of that, that gives me the rights to do this. So if this is equal to, if omega is equal to this whole infinite function, then we get, we can do a substitution like this, and then substitute our outside into our inside. I know that sounds weird, but this is true. So because of that we can do a substitution like this. So pretty much this inside is equal to our outside. Okay? So, or I guess to better visualize, right, we have this that constantly goes forever, but because omega is equal, right, omega, this is equal to this whole thing, which is the same thing as the inside, right, we can just substitute like this. Okay, I know it looks wrong, it looks illegal, this looks really uncomfortable for beginners, but this is true. It is true that the inside is equal to the outside when dealing with infinite functions. Okay, it is true. The inside is equal to the outside when dealing with infinite functions. Okay, but let me clean this. Okay, and now what do we do? You just solve for omega. You solve for omega. You try to isolate omega to one side. All right, this is omega squared, and then divide omega. Oh, would you look at that? Yes, I know. Again, it looks wrong. It looks illegal. But this is indeed true. So, this whole infinite function is just equal to x dx. And so our answer is x squared over 2 plus c. Okay? It's kind of like, think of it as like convergence, right? If you let n to infinity to like however many times whatever, n times, okay, it will converge to equaling, well, 2, right? Or if you do this with any number or any constant inside, it's going to equal to that constant, right? And it's because of this. It's because of algebra. It looks wrong, I know, but this is indeed true, and you have to get used to it. Okay, you just have to get used to it. So you'll become more comfortable. But then again, this is very satisfying to do in integration B. Okay. So how do we apply the same concept with this integral? It's same thing, right? You let this equal to a constant, or I'm sorry, omega, some function, right? And then, okay, this is equal to x square root of x plus square root of x plus square root of x plus, and it just repeats, oh, well, the inside is the same thing as the outside, right? So we technically have this. And then we solve for omega. So I'm going to put it at the top, omega square minus omega, and then equals to x. Okay, but how do we solve for omega? Right, we're not looking for omega square minus omega. We're looking for omega itself. Right, what does this equal? What is omega? Right, because we want to simplify this function. Right, this infinite function has two forms: itself and the simplified version. What's the simplified version? That's what we're trying to solve. But here, we end up with omega square minus omega. I'm going to do minus x 0. And now you can see, to deal with something like this, we can use the quadratic formula. So omega is equal, and then use the quadratic formula. We have 1 plus or minus square root of 1 minus 4ac. That's going to give me plus 4x all over 2. So this integral is going to give me this. But now you're probably thinking, wait, but Silver, something's not right here. You're probably thinking, is it plus or minus? And you know that this does indeed matter. You can't just be like, oh, it's just it's always positive. No, right? This does matter. And the way we determine this is by our bounds. Okay? If you do come across integration bees where they don't have bounds and you're just stuck with a situation like this, assume it's positive. Just assume it's positive. Okay? So that you don't have to deal with people's controversy. But I do believe that it does matter depending on the bounds. So in this case, our bounds are positive, so we will be using plus. Okay, let's go ahead. Plus for x over 2 dx. Okay. All right. And now this is just, it's just basic integration. This is going to be 1, because the half, plus, let's see, a half of what? That's going to be 2/3. Oh crap, that 4 though. Don't forget about that, 4x. X plus 1, 3 half, 0 to 2. Plug in 0, and go like this. Plug in 2, we get 9, 3 to the power 3, divided by 3, we still get 3 squared. 9 over 2, 9/4, minus, and then plug in 0, we get 1, 1, let's see, so everything's 1 here. That cancels out, we get 1 over 12. Is that correct? Times 3, 27, 26. 26 over 12? Is that right? 26 over 12? Which becomes 6, 13. Oh, okay, and then plus 1. Right, and this gives me 19 over 6. And that's our answer. Ooh, if you're a math Olympiad, you already know what the answer to this integral is. If you're not a math Olympiad like me, that's okay. We can still solve this, right? This is omega 1 of 1 plus, and then the inside is equal to its outside. Okay? And then we end up with w squared plus w minus 1. Right? And if we do quadratic formula, we get -1 plus, because we have positive bounds. And then we have b squared minus 4ac all over 2. Oh, this is a constant. This is equal to a constant. This is square root of 5 minus 1 over 2. Wait a minute, this is 1 over the golden ratio. So this integral is equal to 1 over the golden ratio. So the answer is 1 over the golden ratio, 1 over phi. Okay? Very fast. Very, very fast. Okay? You just have to get comfortable with dealing with infinite functions. Honestly, now I think about it, whenever we have some function and we deal with quadratics like this, or let's say we have an x here, something like that, I believe we can't really have a negative bound. Now I think about it, we can't really have a negative bound, because if we do have an x inside the square root and the inside the square root becomes negative, then we end up with a complex value, and that's bad. It won't, either it's not going to converge, or you'll just end up with something not in the domain of the bounds. So just be very careful, just be cautious with that. But yeah, other than that, most integration bees, they should know that it's just positive values only. Okay? Oh god, now we're dealing with trig now. How do we deal with this? So we have an infinite function of sines. So we have omega equal to sine of pi over 3 and then omega. So, I mean, we know that omega is equal to 0. But wait a minute. If all of this is 0, does this equal to 0? Or does it not? So, you must be very, very careful. Sometimes you can have multiple solutions. In this case, let's see. 1, no. Plug in 3, no. Let's see. Plug in 1/2. Wait a minute. Omega equals to 1/2 as well. Sine of pi over 6 does equal to 1/2. Okay, so be very careful. Be very careful. In fact, I think negative works too. A negative half, right? Negative pi over 6. Oh yeah, that should work too. So negative 1/2 as well. However, since our domain is from 0 to 3, our intervals, our bounds is from 0 to 3, I don't think we have to worry about this. It's most likely this positive bound here, right? Otherwise, it wouldn't make sense to have a negative. So, in that case, the actual answer we have is from 0 to 3, we actually have 1/2 dx. Okay? You can't have 0, because if it's 0, then everything's 0. That's too sus. In fact, if you, well, I don't know what the graph of this looks like. I don't know if I want to graph it, but, you know, for sure we know that there is indeed a non-zero solution to this infinite function equation. So because of that, we have to take into account of this portion here. So because of that, we can assume this is equal to 1/2, and this is our answer is 3/2. Okay. Now you might have seen this before if you go to Cambridge University. If not, that's okay. This looks weird, right? You're probably thinking, okay, how on earth does this work, right? So how do you deal with an integral related infinite function, right? Now the bounds are infinite. How does this work? How do we deal with this? It's not just the function that's infinite, it's the integral. The bound is infinite. So how do we deal with this? So what we do, it's like the same, it's kind of the same procedure, technically. However, you might be a little stuck on how you would apply this. But for those, if you have gotten it, yes, you let this equal to I, and what you do is you let 1, and then you let this equal to I. So pretty much our outside is equal to our inside. I think that's like the greatest concept to remember is when you're dealing with infinite functions, the inside is equal to its outside. So in this case, we found the inside is located here. Okay, so we let something equal the outside and locate where the inside of the, where the infinite function recurs to. So here we have this integral here. And so now we go ahead and integrate this with respect to I. So I is equal to, well, this is x squared over 2. So we're going to have I squared minus 1. Right? And this is going to equal to I squared, let's see, 2I minus 2I minus 1 equal to 0. Right? I is equal to 2 plus. It wouldn't make sense to have a negative since this is 1 to somewhere, so this is going to be positive bounded. So we have b squared minus 4ac all over 2. Let's see, this is going to be 2 plus 2 root 2 over 2. This is equal to 1 plus root 2. Our I is literally equal to this integral here. So our answer is 1 plus square root of 2. Okay, it's a very cool, interesting case. So we have another cool integral. So I made this integral for Stanford Math Tournament Integration Bee. And in this portion here, now you might be intimidated where we're dealing with two functions now. So what do? Don't freak out. All right, do the same process. Start little by little steps. Omega square root of sine of x. If we have to, don't worry. We should be fine with tangent of x as well. And then, it recurs the inside. Okay. So now what? So again, we simplify. All right, now we try our best to solve for w. The w squared, we have sine of x. Okay? And then we're left off with tangent x w. Okay, square it again, no worries. We have sine square. And then we have tangent of x. And then we can divide w here. So we have w cubed. And if you notice, we technically have sine cubed over cosine of x. So what we have is that in this infinite function here, omega is equal, this infinite function is equal to sine of x over the cube root of cosine of x. Aha! Alright, so that's what we're going to do. Alright, we found so we simplified our infinite function. Nice. Now we can easily integrate this. So this whole integral is equal to sine of x over the cube root of cosine of x. And we can easily integrate this by u substitution, right? Let u equal cosine of x. This is going to give you a negative du of cube root of u. If you need to, you can rewrite this as negative 1/3 to help you see. And so now this integral, this is like what, plus 1 minus, plus 1 2/3, right? So that's going to be 3/2. So it's going to be negative 3/2. U 2/3, right? I believe that's what we have. I'm just double checking, make sure I don't do this incorrectly, right? Plus 1, we get 2/3, 3/2. Yep. So our answer should be cosine of x of 2/3 plus c. Okay, that's our answer. So that's our last. That was our last integral. So again, getting used to the algebraic way of simplifying infinite functions, right? A great thing to remember. The outside, or when dealing with infinite functions, the inside is equal to its outside. Okay, the reoccurring function in the inside is equal to the outside of the infinite function. So keep that in mind. All right. Other than that, it's very satisfying. It's very satisfying to simplify for the integral. Okay. All right. I hope you guys enjoy that. Practice that, and I hope that was helpful. So thank you guys so much for watching, and I'll see you guys in the next part.